Alright, I've been trying to think of the best way to cover section 3.10, which is related rates, and I think the best way to do it is to pick one of the most common styles of problems and just work through the whole thing. It might take a couple videos, it's a three-parter. The most important thing is that you get an understanding for how to approach these problems, because they can seem kind of daunting. So anyhow, right here what we have is a ladder that's 25 feet in length, and it's been sliding like this, like sliding down the house and out into the yard. And we've moved to a point to where if you project it, in other words, if you shine the light directly down the y-axis, the 25-foot ladder would cast a 24-foot shadow on x. Now, they don't tell us that this side is 7, but if you know two sides of a triangle that's a right triangle, you can always solve the third side using Pythagorean theorem, as I did up here. If they've also given us the rate of change of this segment of the ladder. In other words, this part that's moving in the x direction that way is moving at a rate of 7 feet per second. The question is how fast is the ladder falling? That's dy dt. So it's important to realize that displacement, or how far something is, the derivative of displacement with respect to time is velocity, and that's how fast. That's what your speed is. That could be in meters per second, or in this case, in feet per second. So dy dt indicates the rate of change of the displacement with respect to time in the y direction. Dx dt represents the rate of change of the displacement in the y direction. So the next step here is to find a master equation, which is probably the most crucial step to this process of related rates. And whenever I see triangles, I usually think Pythagorean theorem, so it's important that we find an equation that we can write arbitrarily. And in this case, instead of calling this 24 feet and this 7 feet, let's go ahead and call this x, and we'll call 7 y. And we'll go ahead and write an equation of Pythagorean theorem, because the length of the ladder is always 25 feet. So therefore we know that x squared plus y squared must equal 25 squared. And 25 squared is 625. And then we're left with x squared plus y squared equals 625. Well, the question is, how can we use the information they gave us about the rates of change to solve this problem? And so how we do that is we're going to take the derivative of both sides with respect to time. I'm just going to write this as d dt with brackets around the whole equation. The derivative with respect to time of x squared is 2x. But then we have to remember that in this problem, y is a function of time and x is a function of time. Because when things move and we find a velocity, it's a function of time. And because they're functions of time, they are dependent on time. And time in this case is the independent variable. Time's flow doesn't care about where your position is, but your position definitely cares about how time flows. And so because x is a function of t, we took the derivative of the outer function, which was x squared. But because x is dependent on t, we have to respect the chain rule and take the derivative of the inner function. And the derivative of the inner function is dx dt. So 2x, that's the power rule, times the derivative of what's inside x, which is dx dt. We do the same thing with y. We end up with 2y dy dt, because y is also dependent on t. And 625 is just a constant, so a derivative with respect to anything for this constant is going to lead us to 0. Alright, now it's a plug and chug problem. So we know x is 24. The projection of the ladder on the x-axis is 24. So we have 2 times 24 times dx dt, which is given to us as 7. And then we have plus, let's see here, plus 2 times the y projection of the ladder, which is 7, times dy dt, which we don't know, that's what we're solving for. And that'll equal 0. So we're going to go ahead and multiply through and simplify and solve for dy dt. So 2 times 24 times 7 is 336. I'm going to subtract that to the other side. 2 times 7 is 14. So 14 dy dt equals negative 336. Now I'll divide both sides by 14. And I end up finding that my rate of change in the y direction of the ladder, dy dt, is equal to negative 24 feet per second. So that is part A. Now this is a three-parter, and it's good practice for finding a master equation. For this one, Pythagorean theorem worked just great. The next question is, the area is changing at blank feet squared per second. So the question is the area inside of the triangle that the ladder and the walls and floors make angles with. What area? How is the area changing at this instant in time? And I want to make sure that you know this is very important. We are actually only solving for these parameters at this specific point in time. That's the point in time where we have 24 feet of the ladder in the x direction, 7 feet in the y direction, and a dx dt of 7 feet per second. As this thing was falling initially, there was a lot more going on than just this snapshot that we're looking at. And there's other classes that get into how you can model the whole drop. But right now we're just learning how to find a master equation and solve problems when we know certain parameters. Alright, so there's A. The next one is about area. And any ideas about what the master equation might be for that? It's area, right? It's area of a triangle. So let's go ahead and write the equation of the area of a triangle. Area equals base times width, or base times height, however you want to say it. Either way, our base here is clearly the x component. So the x component is the base. The y component, and I'm sorry, the area of a triangle is 1/2 base times width, because a rectangle is base times width, and a right triangle, or any triangle, is always 1/2 of a rectangle or a parallelogram. So 1/2 base times width is area. We can replace the base with x to make the equation better fit our parameters. The height is y, and so we have 1/2 xy is equal to area. Now we're asking about the rate of change of area with respect to time. So what we're going to go ahead and do is we're going to take the derivative of a with respect to time. Now the derivative of a variable is just the number in front of it. So in other words, derivative with respect to x of 2x is just 2. So the derivative of a with respect to time is just 1. But because area is a function of time, we have to multiply the derivative of the inner function respecting the chain rule. So it's 1 times dA dt. We're going to go ahead and ignore the 1 because it's not going to do anything. It's the multiplicative identity. So next we're going to look here and say, okay, we're taking the derivative with respect to time of x times y. And remember, because derivatives are a linear function, we can pull the 1/2 out front and deal with it later. Alright, so what's next? Well, we have two variables multiplied together like a product. And whenever we see products, we should think the product rule. So outside of this 1/2, I'm going to have first d second plus second d first. First is x. D second is 1 times dy dt, because of the chain rule, plus second, which is y. D first, derivative with respect to time of x is 1 times dx dt, because x is a dependent variable. So this is y times dx dt And here's our equation right here. It's dA dt equals 1/2 times the quantity x dy dt plus y dx dt. And we have all the information we need, so we can go ahead and plug it in. We know at this instant in time, x is 24, and that dx dt is 7 feet per second, plus y, which is 7, the projection of the ladder on the y-axis, and I'm sorry, dx dt is over here, and that's equal to 7 feet per second. Dy dt we solved for last problem, and I forgot to write it down. It's negative 24 feet per second. That's kind of interesting. These numbers are matching up nicely. And all of that is times 1/2. So x 24 times dy dt, which we solved to be negative 24, plus y, which is 7, times dx dt, which is 7. 24 times 24, that's negative 576, plus 7 squared is 49. And this is all times 1/2 and equal to dA dt. So 576 negative plus 49 is 527. And then we're going to divide that, negative 527 divide 2. So dA dt at this instant in time with these parameters is equal to negative 527 over 2. And that's in square feet. Feet squared. Let's go ahead and plug that in. See if it likes it. Oh, and by the way, I'm sorry, I got my units screwed up there. This is not just a static area, because this is the change in area with respect to time. This is feet squared per second. So in other words, what this tells us is how rapidly is the amount of area inscribed by this ladder changing in time. And that's what dA dt stands for. I hope this was helpful. There's a part C to this problem, but this video is getting a little long. If you're interested in seeing that one, let me know, and I'll work on it. Thank you. Bye.